present joint work with Silvan, Sievers and Katz, and we are talking about reachability, and the question we are working on is which atoms can become true in the reachable part of the state space of a classical planning problem. And this question is relevant, for example, for the grounding process, what atoms actually to instantiate, not to blow up the thing too much. It's also relevant for finding mutexes if we don't consider single atoms but pairs of atoms, and mutexes are, for example, used for transformation into finite domain representation or also for strengthening heuristics. And the problem with this is that asking whether an atom is reachable is as hard as the planning problem because we can always introduce a new goal atom that is only reachable like with an action that has a precondition that the original goal was reached. And therefore, for deciding such, or for using the reachability analysis, usually applies some relaxation-based over-approximation. Now, here we don't want to come up with new ways to find reachable atoms, but what we want to do is to speed up previous techniques. And I will use this example task here. It has 4 locations, A, B, C, D, 5 trucks, 3 packages that need to be transported. And if we look, for example, at the blue truck, we see, okay, it can move to C, it can move to B, it can move to D. So the atoms that can be true is blue truck at D, blue truck at C, and at B. And now for us, it's totally obvious that exactly the same analysis applies to the orange truck and the red truck. But the algorithms are not aware of this. They would just repeat basically the same analysis again for these trucks to create the result. And this is what we would like to avoid. So our idea is to perform such a reachability analysis for fewer trucks and fewer packages. And since we are only talking about reachability, the goal is absolutely unimportant for us, so let's forget about the goal destinations of the packages. And what we want to do is get rid of some of the objects. So can get rid of a package, some of the trucks, so that's what we call a reduction. And then we will perform the reachability analysis just on the smaller task, and for example get the information the blue truck can only reach B, C, and D. And then we want to extract from this result the full original result and derive that all the orange and the red track can only be at these locations. So that's what we're aiming for, but this is only the truck example. So in a more general picture, what we want to do is we want to replace this original chain of we get the original task, do the reachability analysis, and get the reachable atoms by some detour, with the hope that this detour nevertheless speeds up the entire thing. So what we do is we first apply a reduction to the original task, get a smaller task, then we apply the same reachability analysis, really just plugging it into the same algorithms and get the reachable atoms of the smaller task, and afterwards we take this result and expand it to extract the original result for this. This is what we are aiming for. And the ingredients we will use for this are symmetry, reduction, and expansion. And here we consider a very simple notion of symmetry, and we define it on a lifted task representation where we have schematic operators like in most PDDL domains, because we also want to use it for grounding, and because on the lifted representation all this analysis is easier, and we can actually more easily reduce the task. And as I already said, since we only talk about reachability, we don't need to consider the goal. So after we have thrown the goal away, we just say that 2 objects are symmetric to each other. If we swapping them in the task description, basically does not change the task description. So it just changes the ordering of operators, for example, or of the initial state. So whenever this is the case, the 2 objects are symmetric, and we extend this to what we call symmetric constant sets. These are just sets of pairwise symmetric objects. So if we have a look here at the example, obviously if we swap the blue and the red truck, well, we don't change anything fundamental about the domain, so we can do this. These are symmetric. Same with the orange. So these 3 are pairwise symmetric. You can combine them in one symmetric constant set. Same for these 2 trucks, or for example, for these 2 packages. And this is symmetry that we will exploit to make all this working. And now the next thing we need is like, how does the reduction work? How does the expansion work? And for the reduction, we consider sets of objects, set C prime, which is a subset of a set C, so constant sets, and the reduction from C to C prime of the task just removes all parts of the graph of the task with occurrences of these objects from C set minus C prime. So as an example, if we apply the reduction from the set of these 3 trucks to only the blue truck on our task, this is just the same as throwing these two other trucks away. So the C prime is the part of C that we want to preserve in the smaller task. Okay, that's reduction. Expansion, the idea is to get back the original results, and what it does is if we have a set of atoms, it also works for literals, then we extend the set in all ways by taking out one of the atoms from the set and just applying permutations on this object set C on this literal. And all kinds of literal we can construct by this are in the expansion of the set. So for example here, if we expand the set where we have P010202 and Q0104 with this object set 010203, well, we take P010202 and now we can replace all objects that occur in the set with any other object from this set, but what we need to preserve is that it must be a permutation. So if the first and the second argument are different, they must stay different, and if 2 arguments are the same, they must stay the same. So for example here, in this atom here, we just replaced O2 with O3, whereas here in this one, we replaced O1 with O3 and O2 at all occurrences with O1. And if an object does not occur in the set, it just is preserved. That's why we have always O4 here for the Q cases. So that's the expansion. And well, the idea we had is that the reduction and expansion are just like inverse operations, and this is obviously not in general the case. The question is, when is it the case? So what we have is that if we consider a C-symmetric set of atoms, so it's a set of atoms which can't be extended by an expansion with C, or put differently, if we have an atom in the set, all symmetric ones with respect to C are also included in the set. If we have such a situation, then applying a reduction followed by an expansion will never introduce new literals. And the question is, when can we really exactly get back the original set? And this is the case if we preserved a sufficient number of objects in the reduction. And what does sufficient mean? A sufficient number is just the maximal number of different objects that occur together in any atom or literal in the set. So that's just to clarify the relationship between reduction and expansion. Now, going back to our original idea, we wanted to have this cycle where we do not directly apply the reachability algorithm, but first apply reduction, then do the analysis, and followed by an expansion. So when can we do this? How far can we get with our reductions? And for this, we defined bounds on the number of elements of a symmetric constant set that must be preserved. And the exact bounds depend on the kind of reachability analysis we want to perform. We will see a few examples. But all of the bounds use kind of sub-bounds. We have a bound on the literals, which is just an upper bound on the number of objects from C that can occur together in any reachable literal, any reachable ground literal of the task. And we have similar bounds for the operators and for the axioms, just upper bounds of what can occur together. And here's the first example of a reachability system we considered. It's basically, think of HMax, so don't read the details, think just of the analysis that is done by the HMax heuristic. So everything that's finite there, get a finite heuristic estimate, would be considered reachable here. And the important thing here is just how many objects do we need to preserve, and this is just the maximum of these individual bounds on the literals operators that we can determine from literals, operators, and axioms. Another reachability notion we consider is pairs of literals or pairs of atoms also, consider both, which correspond to the H2 mutexes. And here we get as a bound that it's like as the previous bound plus accounting once for the bound on object occurrences within a literal. So these are the results we get. We have made a few other contributions. So the question was how to find symmetric constant sets. Well, if you read the paper, you will see that we tried to crack nuts with a sledgehammer and use the full power of structural symmetries, using Bliss and whatever on this. But as Stefan correctly pointed out in the HS-DIP workshop, if the domain is totally not mentioning any constant, we can just try it out in the initial state, swapping two objects, is it symmetric or not. So we could have performed a simpler way, and we just like analysis for pairs of constants, whether they are symmetric, and finding the symmetric constant sense is just a simple union find algorithm. Next question is how to come up with these upper bound, and that's a crucial part in this entire approach, because we want to have tight upper bounds on these, for example, number of objects that can occur together in an operator, because a tighter bound means that we can have a stronger, more pronounced reduction. And for this we used a logic program which again just applied a very severe over-approximation, again based on a relaxation, very roughly going through. So that ran very quickly, but it gave us better bounds than just having a look on the individual operators. The last contribution is, so far I only spoke about one set of symmetric constant sets. What if we have several ones, like these 3 trucks on this side, 2 trucks here, and there it turns out that it's totally unproblematic as long as these sets are disjoint, which is naturally the case, otherwise we would just have a larger group. Okay, so this is like the theory part. We have tried the approach. For this we implemented it in the translator component of fast downward. For the reachability used for grounding, we just used the existing algorithm. For the H2 mutexes, we added a logic program which does the analysis. For our experiments, we have used what we found from the IPC benchmark. So we had a look at 77 domains from the sequential tracks. We also, in this entire work, which made all the write-up much more complicated, we also considered the full PDDL set, like full classical PDDL set, including axioms, conditional effects, all quantified effects, everything. And an analysis of these domains revealed that of the 77 domains, 51 domains exhibit tasks with symmetric objects or non-trivial symmetric objects, and applying this technique for grounding basically showed that it's applicable for 1,004 tasks from 49 domains, so like most of them where there are such symmetries, but an analysis of the timing just showed that the approach doesn't pay off. It's not faster than the previous one, and the main reason is that a reachability analysis performed for grounding is already very, very fast, and this entire runtime is dominated by actually generating the set of reachable atoms, just because this set is comparatively large, and we need to generate it at the end because it's the result. For the H2 mutexes, we could apply a reduction to 610 tasks from 38 domains, and here is the runtime. So this is H2 mutexes on pairs of atoms, and it's a full runtime. So this compares the runtime like on the regular task, just applying the reachability analysis compared to the full cycle using computing symmetric constant sets, applying the reduction, doing the reachability analysis, and expanding the result. And as you see, we can be orders of magnitude faster. And this is not only true on this like somewhat pathological domains like gripper or child's neck. So these are there as well, but it's also a large number of other not so like structured domains. So to sum up, what we have done is we have used symmetric constant sets for reducing the size of a task, applying a reachability analysis, and expanding the result to get the same result as we would have just gotten with a a simple reachability analysis on the original task, and the idea is to be much faster for this because we need to consider much smaller tasks in the reachability analysis. For future work, if you read the paper, you will see that we concentrated a lot on these particular reachability systems for grounding and for H2 mutatixes. Basically, when we pressed the submit button for the camera-ready copy, we noticed, well, we should have formulated in a much more general fashion from the very beginning, because then it would be just more widely applicable, and it's easy to generalize it because it always uses the same principles. Another thing we noticed in recent work by Jussi Rintanen on schematic invariance by reductions to ground invariance, that in there he has also a limited instantiation, and I don't want to go into the details because it just types and things like that, but on a closer examination we see that he basically used exactly the same bounds as we used, but for a different thing. So Jussi was considering regression-based invariance synthesis. And well, one guess is that we just looked at the same creature from two different angles and need to find out what's really going on there, what is the common thing. So I would like to clarify a relationship to this work and see whether we can just apply this symmetry-based reduction on a wider scale to a larger number of invariance synthesis algorithms. That's it. Thank you.
Okay, questions?
Did you think about the problems that arise when you slightly disguise the symmetries and it ends up undermining your algorithm? So when we thought about symmetries, we thought a lot about them almost symmetries. So for example, in your trucks problem, if you name all the drivers and you say this is the driver for this truck and this is the driver for that truck, even if it doesn't appear anywhere else in your problem, so it's not relevant to your action, it breaks your algorithm because you now say, oh, if I swap the trucks around, it changes the problem because there's different drivers now. So I end up losing all of those symmetries, even though they're actually irrelevant constraints. So have you thought about that kind of problem at all?
Well, I just briefly recall the question for the recording. The question was whether you have considered the problem that often the formulation of the domain of the task just kind of breaks accidentally symmetries, and that we could kind of how we can handle the situation. We haven't looked deeply into that yet, so some of this can be probably handled because we use this larger scale of full structural symmetries where we can do several mappings at the same time, but we haven't applied it yet here, so I can't finally answer it.
Can you also use this for relaxed planning rather than just relaxed reachability analysis? Can you extract relaxed plan?
I just know I don't know. What we have is we can't really talk about states, like what can be true together, but I think in the terms like what Hmax does style-like things, we can do it because there we just symmetric things just propagate through the layers of the graph symmetrically. There it would be possible, yes.
I'm asking because it seems halfway to the lifted relaxed planning things that I done at KCL a few years back. Maybe you can finally make lifted planning a reality sometime.
Let's have a look into that.
Okay, any other questions? There's still time. Oh, yes. I'm not very sportive. Okay, you want me to throw it? Okay, here.
There we go. Yeah, I was wondering, there's sort of a cool idea that I thought might come out of this is, can you actually plan in the reduced domain? It's still a real domain, right? Like you could do the symmetry reduction, ground, and actually plan in the reduced domain? Because then you could do something where you end up with something like macro actions for each of these symmetric objects if there is somehow a goal associated with them.
It's not so simple because we have this delete relaxation in here, so it's not that we can, like,
But the symmetry reduction doesn't rely on the delete relaxation, does it?
So here we can only apply to reachability because reachability is a symmetric thing. If we can reach an atom within one step, we can reach all symmetric atoms within one step. So that's easy in this part. But if we wanted to reason about what we can reach together, it's much harder. But Micha, who is a co-author, seems to want to comment on that.
Well done. Can I?
If you can throw it, yeah, okay. Yay.
Great. So, as Gabby mentioned, this doesn't stabilize the goal, right? So if you stabilize both the initial state and the goal, you'll get only those objects that are completely symmetric, so completely interchangeable. So that's partially answers Jörg's question as well, I guess. So we should think about how not to stabilize the goal and still be able to consider the goal with the reduced task. Because those symmetric objects would still have different goals in the reduced task. Right?
Okay, let's take the rest of the discussion offline, please. Thank you. Gabi again.